So let's say we want to sort an array in JavaScript. We can use a built-in sort method like so. And in this case we get a correct result. But watch what happens if we add just one more number. Now we're getting something that doesn't make sense. How is it possible? How could 11 be less than 2? If you guessed conversion to string, you'd be correct. When comparing two elements, JavaScript first turns them into strings and then compares those strings. Since the first symbol of 3 turns out to be larger than the first symbol of 11, it decides that string 3 is larger than string 11. So it concludes that 3 must be larger than 11. This is not a bug, it's an intentional behavior set in ECMAScript standard. Here it is. So let's take a look at why this behavior makes sense in JavaScript and how to sort elements properly depending on their type. And as a bonus, we'll learn a few tricks for optimizing performance of any JavaScript code. JavaScript arrays are special. Unlike arrays in languages like C and Java, which are strictly typed, they can contain a mixed bag of things. With arrays like that, you might need to compare a number to a string or a boolean. Normally, you would leave this kind of work to the user of the sort function, but to provide a sensible default behavior, we need to convert elements into the same type. Converting into strings turns out to be a good choice, since all values in JavaScript have a toString method. But why bother with string conversion at all? Why not just use operators like greater than or less than? They can compare different types, right? Well, sort of, but there is a catch. Let me ask you this. Is 1 smaller than the word 3? Like spelled out 3? No? Is it larger than? Also no? Must be equal then, right? Okay, so what the hell? What happens here is also a type conversion, but in this case JavaScript tries to convert into a number. When the string is an actual number, it correctly returns a number. But when the string doesn't contain a number, it returns nan, which stands for not a number and represents an undefined number. And when you try to compare nan to anything, the result is always false. It's not even equal to itself. This creates a problem for a sorting algorithm. Since we can't consistently compare two values, we can't guarantee a consistent sorting result. The result will depend on the order of the elements in the input array. So instead, JavaScript uses a conversion to string. It's not perfect, but at least comparing two strings gives you consistent results. But you really shouldn't rely on the default behavior when sorting things in JavaScript. The proper way is to provide your own compare function, which will be called every time the sorting algorithm needs to compare two elements. This compare function should take two arguments, both of the elements of the array, and it should return a positive number if the first one is larger than the second one, a negative number if the first one is smaller than the second one, or 0 if they are equal. If you are sorting an array of numbers, this can be shortened to just returning first minus second. There actually is a better way to sort numbers, which we'll get to in a second, but for now this is good enough, and it finally gives us the correct answer to the earlier example. Same approach can be used when sorting an array of objects. For example, in this list of humans there are dates of births and numbers, so we create a compare function which compares their dates of births. One thing to note is this function might be called multiple times per element, so you should avoid doing any complex calculations in here. We'll take a look at how to handle this later in the video. Also, compare functions should be pure, meaning it shouldn't mutate the objects being compared or anything outside of the function. Okay, so we need this compare function for numbers and various types of objects. But what if we are sorting an array of strings? Since the default behavior is to convert to strings, we don't need to use the compare function, right? Well, it's not that simple. Consider this example. As you can see, this sorts the array incorrectly.
Éclair
Should come before
phare
since letter E comes before letter F. The reason
éclair
ends up at the end of the list is because the default sort method sorts letters in the same order as they come in the Unicode table. You can see that the letter F is here at the position 102, and all the accented letters come later, including accented E, which is all the way over here at the position 233. So from the sorting function's perspective, F is smaller than accented E, so
phare
should come before.
éclair
And even if you're only sorting ASCII characters, this won't work properly, since all capital letters come before lowercase letters in the Unicode table. So sorting this array puts Charlie at the first spot just because their name starts with a capital letter. To fix this, we need to provide a compare function to the sorting algorithm. Luckily, we don't have to know all the intricacies of all the possible languages our program might encounter. We can use a collator class to compare strings for us. We create a collator object and use its compare method inside our compare function. And just like that, we're getting a correct order of our strings. Sometimes you'll need to specify which language you want to be used for the comparison. Like in this example, the city name of
Ängelholm
ends up at the start of the list for German and at the end of the list for Swedish. Collator also takes a ton of cool options. Like you can tell it to ignore punctuation and treat numbers inside the strings as actual numbers, which allow us to sort strings with numbers embedded in them. You can see how users end up in the correct order here on the right. Okay, so now that we know how to sort strings, let's take a look at numbers. If we have an array of numbers, a very simple compare function will do the job, as we've seen before. However, if you want to get maximum performance out of your code, you can use a typed array. Typed arrays allow us to treat data inside them as numbers of a specific type, and just like normal arrays, they have a built-in sort method. So first we need to convert our normal array of numbers into a typed array, then we call a sort method on it, and then we convert it back into a normal array. This sort method works differently from what we've seen before. Since it knows the type of numbers it's going to be sorting, it can use a C++ standard sort function. Here in V8 source code, you can see that it checks if it has a compare function, and if it doesn't, it calls this typed array sort fast function, which will eventually call a C++ standard sort. I found this approach to be quite a bit faster than normal array sort, even taking into account the time we spent converting our numbers into typed array and back. You can use any of the typed arrays depending on the numbers you are sorting, but you need to choose the one that will fit the largest element in your data. Like in this example here, if you use int8array, which only allows 1 byte per number, but try to sort larger numbers, the results are unexpected. If you are not sure what kind of numbers your program will sort, just use float64array, since all the numbers in JavaScript are actually float64s. Now let's step back to sorting objects for a second. Remember how I said you shouldn't do complex calculations in your compare function? For example, here we have a list of students and a list of their grades for each student. Let's sort this list by students' average grades. We'll calculate the average grade for each student inside our compare function, and since averages are numbers, we can just return first average minus second average. We get a correct result, but our compare function might get called multiple times per student, which means we will be calculating the average grade multiple times per student. To improve this, we can use a technique called decorate, sort, undecorate. First, let's go over the array of students, calculate the average grade for each one, and save it together with the index of the student. This gives us this array of average grades and corresponding students' positions in the input array. This is our decorate step. Next, let's sort this array of average grades using a simple compare function. This is obviously the sort step. Finally, since we know which grade corresponds to which student, we can reassemble the array of students in the sorted order. This is the undecorate step. By doing these extra steps, we guarantee that we calculate the average grade only once per student, and our compare function only does a simple comparison and no heavy lifting. Let's try to improve the performance of this by eliminating the compare function altogether. Just like before, we iterate over students and calculate the average grade for each of them. This time, however, we add this average grade into a typed array. This is what we'll be sorting later. Since typed arrays only understand numbers, we'll need to do some extra bookkeeping. Let's create an object called grades and use it to store the relationship between the average grades and a particular student. So at the end of the decorate step, we have a typed array containing all the average grades and a map which keeps the connection between each average grade and a specific student. Next, a very simple step of sorting our typed array. We don't provide a compare function, so we can take advantage of very fast sorting by C++ standard sort. Finally, we need to reassemble our initial array in the sorted order. We go over our sorted typed array of average grades, take corresponding students, and put them back into our original list. And now we have our sorted list of students. This method can be a lot faster than built-in array sort. Like in this example, it is 2.5 times faster. On the other hand, in this example, it's almost twice as slow as built-in sort. If you look closely, you'll notice that the performance of our typed array method didn't change a lot between two examples. But built-in array sort is almost 6 times faster than in the second example. In both cases, the number of sorted elements is the same, so why is performance so drastically different? Well, in the first example, we are sorting an array of very diverse objects. You can see here how each object has a uniquely named property. But in the second example, we are sorting a collection of uniform objects. Each object has an ID property and a value property, and nothing else. To understand why this makes such a huge difference, we need to take a peek into how JavaScript engines optimize our code. I'm going to talk specifically about V8, which powers Node and Chrome, but other engines make similar optimizations. Don't worry, I'll try to keep it simple, and I promise it'll be worth it. So when we run our JavaScript program, it gets parsed, compiled into bytecode, and passed to the interpreter. The interpreter reads the bytecode and executes it step by step while collecting information about the function calls and value types. Now, JavaScript is dynamically typed, so we as programmers don't have to deal with types for the most part. But internally, V8 keeps track of objects' types by assigning each object a hidden class. A hidden class stores metadata about its object, including object's shape, meaning which properties does it have and where they are stored. If we assign another property to the object, it gets a new hidden class. Property order does matter as well, so if we swap these properties places, our object gets yet another hidden class. Most importantly, objects with the same shape will have the same hidden class. So these two objects will have the same hidden class, but if we add another property to the second object, its hidden class will change. So how does this help V8 speed up our code? Well, this information about properties and their locations allow us to optimize one of the most common operations in JavaScript, property lookup. So let's take a look at how it works. Here I've generated an array of simple objects. Each of the objects has an X property and a Y property. I've also created this function which does a property lookup, so it takes an object and returns its X property. And we are calling this function for each object in the array. Now let's run this program in Node. We can use a trace opt flag, so Node will show us optimizations that happen while the program is running. What we see here is V8 noticed that we call our lookupX function over and over again and decided to optimize it by passing it over to turbofan, which is V8's optimizing compiler. Turbofan will take our function and compile it into machine code, which runs much faster than running bytecode through the interpreter. Let's take a look at what this machine code looks like. To do that, we can use print_opt_code flag. So this is an assembly version of our compiled function. I've omitted a bunch of instructions here and there. We are only interested in these couple of lines here. This is the JavaScript source code of our function. Every time this function got executed, V8 remembered this object hidden class. In this particular case, all of the objects have the same shape, so it had only seen a single hidden class. And this is exactly what this value is here. This is an address in memory of the hidden class we've seen before. On the next line, we compare this hidden class to the hidden class of the current function argument. So we are essentially asking, does this object has the same shape as the object that we've seen before? If the comparison is true, then we know the exact shape of this object, which means we know where it stores its property values. This means that we can access them directly by the address in memory. And that's exactly what happens on the line 48 here. This +17 is where our property X located inside of an object. As you can see, both the hidden class and the property address are inlined into this code. So if this function ever gets called with an object that has a different hidden class, V8 will have to scrap this code and create new one. Which is exactly what happens if the comparison here fails. This JNZ instruction tells the CPU to jump to line 96, which is a call to deopt procedure. It even says here, deopt reason run map, meaning the object's shape doesn't fit the shape we've expected. This procedure tells V8 to throw out this machine code and go back to executing bytecode through the interpreter. This function might get optimized again in the future, and we'll see what that looks like in a second. But this process of deoptimization is a huge performance hit in and of itself. Now let's see how this generated code changes if we change our input a little bit. Here's a similar array of objects to the one we've seen before. All objects have X and Y properties, but some of them define X first and Y second, while others define Y first and X second. Let's run the exactly same code as before with this array. You can see that our assembly code changed a little. Here's a hidden class that represents an object with an X and a Y property. We check if our object has the same hidden class. If it does, we jump to 7a, where we directly access property X just like before, using a +17 offset inside of an object. However, if the comparison fails, we don't go directly to deoptimize call. Since V8 saw us calling this function with two types of objects, it inlined both of them. So this is a hidden class that represents an object with a Y and an X properties, same properties as the other one, just in a different order. We check if our object fits this hidden class, and if it does, we access the property X by an offset of +1f. Now if this comparison also fails, then we jump to B3, which is a deoptimization call, just like the one we've seen before. This type of code is referred to as polymorphic, as in it deals with multiple potential types of objects. The previous example was monomorphic, meaning it deals with a single type of object. So from here, can we just keep adding more comparisons for every type of object? We could, but this approach doesn't scale well. Since functions arguments can be any number of different types, V8 caps such optimizations at 4 types. So what happens if we call our function with 5 different types? Well, let's take a look. Here's a similar array to the previous ones, except in this one, every single object has a unique named property. We run the same code as before, and here is our optimized function. As you can see, there are no comparisons in this code. Since every object has its own hidden class, V8 gave up and replaced all the inline values with a single function call, which will fetch the value of X for us. This kind of code is referred to as megamorphic. This might seem shorter and simpler than the previous examples, but calling this function is much more expensive than just retrieving the value of the property by its address in memory. In fact, we've already seen how much more expensive. As we've seen before, in this example on the right, we are sorting an array of uniform objects, while on the left we have an array where every object has a unique named property. So on the right, V8 produces monomorphic optimized code, while on the left it's megamorphic, and the difference in performance is around 6-fold. Note that in both cases the code is exactly the same, so is the number of objects. The only thing that is different are the hidden classes of the objects. Whether our input is all uniform objects or not doesn't affect our TypedArray sort much, since the actual sort function deals with the numbers and not objects. Also, it is run entirely on the C++ side. But the built-in sort benefits from being monomorphic a lot, since for every call to compare function it has to do property lookup twice. So optimizing this seemingly simple operation gives a huge increase in performance. As you can imagine, this is true not only for sorting but for any kind of code where you access objects' properties. So if you take away anything from this video, let it be this: write monomorphic code. When creating functions, make sure that each argument takes form of one single hidden class. And when you create an object, define all the properties it should have up front, and don't change the types of those properties while the program is running. So once I learned all of this, I thought to myself, could I just write a sort function in plain JavaScript and rely on V8's optimization to make it super fast? Could it even be faster than the built-in sort function? Well, it turns out it can, sometimes. Here I've coded a quicksort in vanilla JavaScript, and for some datasets it is faster than the built-in sort. Now this is not exactly apples-to-apples comparison. V8 uses a different algorithm for sorting arrays called TimSort. What exactly is TimSort will be the topic of my next video, so subscribe if you don't want to miss it. For now, let's just say it's somewhat slower with some datasets while being much faster with others. Like when we are sorting an array that is already mostly sorted, it wins over my quicksort implementation by a long shot. I've also implemented TimSort in plain JavaScript, and it is generally pretty close in performance to the built-in one. But sometimes even it manages to pull ahead. Like, I don't know what's up with Firefox, but if the input array is partially sorted, vanilla JavaScript implementation beats built-in sort pretty consistently. However, for randomly sorted inputs that is not the case. My point is this: sometimes it makes sense to write your own algorithm in plain JavaScript, as you might get better performance than the built-in function. Just make sure to write your code in a way that makes it easy for optimizing compiler to optimize, meaning keep it monomorphic where possible. And that's all I have about sorting things in JavaScript. I hope you enjoyed and learned something new. Thanks for watching.